I'm Keep, and this is PCBSYNC. Today, we're going to talk about something that a lot of engineers have done before. It looks totally fine on the surface, but actually, it's a big problem. If your board passes testing but fails in mass production and EMI starts going off, it's very likely because of this mistake. So, let's first take a look at a PCB I just designed, a simple microcontroller circuit. This is a standard RF trace, connectors at both ends, and a via in the middle. On top, we have the signal line, and underneath, also in blue, is a continuous ground plane. A lot of engineers see this and think there's nothing special about it. But actually, this is exactly the kind of environment RF loves the most. Now, let's look at another example I drew, this time showing a mistake. A lot of companies tend to do something like this. For example, they'll put some components and traces on the backside. Here, I've used a slot as an example. There's no ground line or ground plane in this area. Maybe a lot of people think this doesn't matter since the signal line still looks intact. So many people assume it should be fine. But engineers start getting headaches as soon as they see this. Why is that? Let's first look at the return current because the F current also wants to go home. And it's especially lazy. It always wants to take the shortest route. For microstrip lines, the return path is directly underneath the microstrip line. So for the line we just talked about, its correct return path is right below it. So in this example, it's like the navigation system showing a clear road ahead. Now, let's look at the previous incorrect example. I dug a slot at this spot, so there's no ground plane here. So what happens when the ground plane is cut? The current suddenly realizes, hey, the highway home has been cut off, so it has to detour all the way around the edge. The farther it detours, the larger the loop area becomes. That's when problems start to show up. Let's take another look at this PCB. So how does the return path go on this board? It can only go down here and loop around from below or loop around from above. Obviously, that's much longer than going straight through the middle. After the ground plane is cut, it causes the return path area to increase. Now, let's take a look at a simulation I did. Here, I used the correct method to simulate the S11 and S21 curves, and you'll notice that some S21 values are very close to 0 dB, which means the performance is quite good. It's pretty good. Then, I also did another one. This is after the S plane was cut. Here's a comparison track. As we can see here, the dashed line represents the implementation without cutting the ground plane. We can see that looking at the S21, its performance is worse. It's further away from 0 dB. There's more attenuation. So this is also quite obvious when you look at the curve. After cutting, the performance drop and impedance transformation are already very noticeable. What's even more troublesome is that this energy doesn't just disappear in the thin air. It turns into radiation, and right at the break, it starts to generate radiated emissions. Then all sorts of mysterious problems start to show up. Congratulations, your EMI package is now automatically activated. Remember this line from today. RF current also wants to go home, and it's especially lazy if you cut off its way home. It'll definitely find its own way, but the path it finds is usually not the one you want. The PCB won't show any errors, but physically, there will definitely be problems. All right, that's all for today's content. Thank you all for watching.